My pleasure to, well, first, before, I always forget to get the community statement. We have a community statement. And so we follow three kind of big guidelines. And so the first one is we're all learning. And what that means is, some of us are more experts on some topics than others. And so we always have something new to learn. And even the speaker doesn't have all the answers. And so we can make an effort to either think of a solution here or think of people that might help us get to the solution. The second one is everyone has something to contribute. Again, we come from, we're all passionate for combinatorics, but we approach it differently. And so everybody has something to contribute. And like I said, the last one is no one has the answers. And so, if somebody gets stuck or people mess up, sometimes I've given a talk where I'm like, wait, I don't even know if I believe what I've written. And so again, not everybody has the answers. And so we want to extend grace and patience. And with that said, I will introduce now, I have the pleasure of introducing my friend, Sophie Rehberg, who is a PhD student at FU Berlin, working with Matthias Beck. And she'll be talking to us about combinatorial reciprocity theorems for generalized Pruned hypergraphs and pruned inside-out polytopes. So let's welcome Sophie.
Yeah, thank you for this very nice and friendly introduction. And thank you also for inviting me. I'm very happy to give this talk, and thank you also for organizing this great colloquium. It's really cool. And second of all, please feel free to interrupt me anytime if you have any question or comment. I'm happy to try to answer. Yeah, and then I have to make a little disclaimer. I probably won't talk about hypergraphs that much today. I've changed my talk kind of last minute, and yeah, I will comment on this later on. So let me first start with a motivation and an example of a combinatorial reciprocity theory, which is this one by Stanley from the 70s. I guess many of you have heard of it. So if you want to count the number of proper M colorings of a graph G, you can prove that this counting function agrees with a polynomial in M of degree D, where D is the number of vertices. What do I mean by a proper coloring? So I assign every vertex a color, and this coloring is proper if colors of adjacent vertices are different, right? So see, V is different if UV is an edge in our graph. Okay, and then something interesting happens if you plug in a negative integer. Well, you still can compute the value of the polynomial, and you can adjust the sign. And then you can prove that this actually also counts something interesting. In this case, the pairs of compatible M colorings and acyclic orientations. So an orientation is just like giving every vertex every edge an orientation, and coloring and then acyclic orientations are compatible if the value of the color increases along the orientation, right? Well, this result is not new, and there are many proofs out there. And one very geometric approach is via inside-out polytopes, which was introduced by Matthias Beck and Thomas Stavslavsky. And here the idea is to kind of identify colorings with integer points. So I have a very small example here. I have a graph with just two vertices, x1 and x2, say. And then if I color, say, this vertex with color 2 and this one with color 3, I will identify it with the point 2, 3. That's right? Yeah. In this plane, right? So what I want to count here are the integer points in the cube. Well, this should be m in my notation, right? Which lies strictly between 0 and m plus 1. And I want to exclude the integer points that lie on this, well, in this case, on the line where x1 equals x2. Right? And then I can do integer point counting in polytopes and apply some Airhead theory. And I will tell you what this is in a minute. Let me first show you some like overview of literature I know that motivated this research. So we have
I have a quick question on the last slide.
Sure.
Should the less than be a less than or equal to?
Yeah, maybe you're right. Yes. No. Yes. Yes. You're right. I don't need here in this case. I don't need the colorings to be proper, so I allow for equal colorings along the edge. Yeah. Thank you. Okay. So I've talked about this reciprocity result by Stanley and how you can just given you an idea how you can prove this using inside-out polytopes and Airhead theory. And there's also a completely different approach via a reciprocity result for generalized Computahedron, which was proved. Well, this like how this reciprocity result for graphs follows from this for generalized Computahedron was proved by Agia and Adlila. And this reciprocity result was first proved by Vilera, Gia, and Reina, but stated in a slightly different language than I will use here. And the goal is to generalize this reciprocity for graphs to hypergraphs. And there is a paper by Aval, Karabogosian, and Tanasser from last year, and they give a reciprocity result, and they also prove this also using some Hopf monoid of hypergraphs. So all this here uses Hopf algebras and Hopf monoids and things like this. So my first question was, okay, if we can use this reciprocity for generalized Computahedron to show the one for graphs, because you can assign to graphs a graphic polytope, and that's a subclass of generalized Computahedron, and then you can apply this. Is this also possible for hypergraphs? Because you can also like define a hypergraphic polytope, and that's a subclass of generalized Computahedron, and so on. And the answer is yes. And I also wanted to find out, well, can we like generalize this inside-out approach to show, well, first my motivation to show this for hypergraph was to show this for hypergraphs, but turns out we can even use what I will call pruned inside-out polytopes to show this reciprocity result for generalized Computahedron using Airhead theory and give a more general version of that. So today I want to talk mainly about this part of like pruned inside-out polytopes and generalized Computahedron, and not, well, depending on timing, maybe I can state the result about hypergraphs, but I won't prove it today. So here's the outline. I will first recall some geometric definitions and what we need for a generalized Computahedron, a very short introduction to Airhead theory, and then I will define pruned inside-out polytopes, and I will show you the application to generalized Computahedron. And the application to hypergraphs, I won't talk about this today, but most likely I will talk in the combinatorial seminar of the Kansas University, and there I will talk about this part. So if you want to know more about hypergraphs, check the homepage and there will be a talk. Okay, so let's get started. First, just to make sure that everybody's on the same page, the definition of a polytope, we take the convex hull of finitely many points. So here's my very small example, 2 dimensions. I have these 5 points, and convex hull means I want to include all connecting line segments between any points, and then, well, recursively any 2 points on the line segments, and so on. And I will this. You can think of this in 2 dimensions, like taking a rubber band and putting it around the 5, in this case, points, and everything inside is your polytope. And a cone is an intersection of half spaces that contains rays. What do I mean by this? So if some point is in my cone C, I also want any positive scalar to be in C. I'm sorry, I should write more carefully. Okay. So this should be in C for all positive scalars. Okay, so which means that here I have the whole ray is contained in this cone. All right. Now let me define what standard Computahedron are. These are polytopes where I take the convex hull of d factorial points, all the permutation points of the point 1, 2 up to d. So here are some examples. Well, this is the point 1, 2, and this is the point 2, 1. And here, let me check to not mess this up. So I start with the point 1, 2, 3 here, and I have 1, 3, 2, 2, 3, 1. Yeah, I guess you get the idea how this works, right? 1, 2, 2, 1, 3. These are all the permutations, and I take the convex hull, and that's my polytope. You can also see that this polytope is of dimension d-1, because if I sum over all the coordinates, this sum will always be constant, right? Because well, I'm always summing up the numbers from 1 to d, right? So this is d plus 1, which is 2. So this is why we can still have this nice picture of the 4th standard Computahedron, because it's actually a 3-dimensional object embedded in the 4-dimensional space. Okay. Let me define some more geometric notions we will need. So I want to call elements in the dual space directions. And then for any direction, I want to define the y maximal phase as being the phase in a polytope where this functional takes maximal value. You can think of this as the usual Euclidean scalar product. So let's look at an example. If I would want to maximize in this direction going straight up, my y maximal phase would be this edge up here. Right? And if I now collect for a fixed phase all the directions that maximize this phase, I get the normal cone. So this would be this ray here for this edge. And then collecting all the normal cones for phases of a polytope, I get the normal fan. This is what I depicted here on the right-hand side in blue. So maybe let's look at one more example. The normal cone of this vertex here would be this 2-dimensional cone over here. You can also think of this as being spanned by the outer normal vectors of the facets. Okay, are there any questions about this? Then let me give you 2 facts about normal cones. So the dimension of the normal cone equals the codimension of the face, right? So it's dimension d minus the dimension of the face. And if f is the face of G, well, then for the normal cones, the relation like turns around. Then the normal cone of G is the face of the normal cone of F, right? So if I look at this vertex, which is a face of this edge, then I get that this ray, which is the normal cone of the edge, is the face of this cone, the normal cone of the vertex. And I want to call directions that have a vertex as y maximal phase. I want to call them generic because they are contained in full dimensional cones in my normal fan. Right? So it makes sense to call them generic. Okay, are there any questions on this? We will work a lot with this maximal phases and normal fans. So, okay, then let me move on and define one very special fan, which is the braid fan. First of all, let's look at the braid arrangement, which is a set of hyperplanes, whereas always set two coordinates to be equal, right? So in the two-dimensional case, I just have one line where x1 equals x2. In the three-dimensional case, I get three hyperplanes, right? x1 equals x2, x2 equals x3, and so on. And you can see that here, this line where all coordinates are equal is contained in all the hyperplanes. So it's contained, it's a phase of this. I shouldn't say a phase. So, and then I define the braid fan, which is the fan induced by the braid arrangement. What do I mean by this? I take the whole space, I take out the hyperplanes, and I get some components which turn out to be cones. So I take the topological closures of the cones, and this will be my fan. So here in this case, I will have 6 two-dimensional cones, right? These ones, these full-dimensional, three-dimensional cones. Then I will have these 6 half spaces, half hyperplanes, and this line in the middle. And they will form my braid fan. Okay, why is this braid fan important to us? Because it's the normal fan of the standard Computahedron, right? So the normal cone corresponding to this vertex would be this cone over here, or the one corresponding to this edge would be this half hyperplane up here. So the braid fan is the normal fan of the standard Computahedron. Okay, and with this at hand, we are ready to define generalized Computahedron. There are several equivalent definitions out there. My favorite one is about normal fans. So I want to call a polytope a generalized Computahedron if its normal fan is a coarsening of the braid fan. By the way, there are different notions of what a generalized Computahedron is. Some people call these things deformed Computahedra, and but yeah, here I want to call them generalized Computahedra. Okay, and a more graphical way of looking at this is saying generalized Computahedra are deformations of the standard Computahedron by translating facets. So what I did in this example here is I moved this facet out, right, in this direction. And as long as this edge still doesn't degenerate, the normal fan would be the same. So I would still have this half hyperplane here. And as soon as these as soon as this edge degenerates into a vertex, what happens in the normal fan is that I glue together these two cones to be one cone. I take the union of them. And this is the coarsening of the braid fan. Okay, are there any questions about generalized Computahedron or Computahedra? Okay, then let me move on to give you a one slide introduction into Airhead Theory. So we want to consider polytopes and positive dilates of polytopes, right? So by dilate, I just mean like dilating every point. So here I have my unit cube, and then the second dilate would be this one, and the third dilate this one. And then I want to count the integer points in every dilate, right? So here, in the first dilate, I would have 4 integer points. In the second, I would have 3 times 3, so 9 integer points. And then the third, I would have 4 times 4. So you can see that in this case of the unit cube, I would get the polynomial t plus 1 squared. And this is no coincidence. So this is a result by Airhead from the 60s, that if I have an integer polytope, which means that all my vertices are integer points, then this counting function is a polynomial of degree d. And even better, there's a reciprocity result. So if I plug in negative integers, what I count is the integer points in the open polytope. Right. So in this case, for the first dilate, I would have no integer point. For the second dilate, I would have 1. For the third dilate, I would have 4. So you can see that this is t minus 1 squared, which is the same as minus 1 squared. Well, I always have to adjust the sign, and minus t plus 1 squared. Right. So this is like the key result we will use to obtain all the following reciprocity results in this talk. Okay, are there any questions? Great. So now let me define the pruned inside-out polytopes. And for this, I first want to define what I call a codimension 1 fan. So for a complete fan, or you can just think of a normal fan, the codimension 1 fan will contain all the cones that have codimension at least 1, which means all the cones that are not full dimensional. Right. So in the case of the normal fan, this means I take normal cones of all faces that are not vertices. Right. So you can see an example here. The codimension 1 fan is always in this dark blue color. So here it would contain of these 3 rays that are not full dimensional. And here I would have these 5 half hyperplanes that correspond to the normal cones of these 5 edges of my polytope. I always think of this codimension 1 fan as a pruned hyperplane arrangement, right? So what happened here is I cut out some part of a hyperplane in the hyperplane arrangement. Right? So for me, these are pruned hyperplane arrangement, which explains the name of pruned inside-out polytopes, because I want to call a pruned inside-out polytope all the points that lie inside a polytope Q, but not on this codimension 1 fan, right? So here's an example. I have this square Q. I have this fan and the codimension 1 fan consisting of these 3 rays. And then my pruned inside-out polytope is this cube without the points on the rays. And then I get connected components, which I call regions. In this case, these regions are half open and half closed, which is really not convenient if you want to do something with it. So we will mostly consider like open pruned inside-out polytopes, where I throw in an open polytope and then I get open regions. It's much nicer to work with. And now I want to define 2 counting functions for these pruned inside-out polytopes, which then will be related by reciprocity. Okay, so the first counting function is the inner pruned Airhead function. I've put the formal definition up here, but you can also just look at the picture. So what I want to count is, I want to count the integer points in my pruned inside-out polytope, so that are inside the polytope, but not on these codimension 1 cones, right? And again, it's much more convenient to do this for open pruned inside-out polytopes, because you might see that then my regions are open polytopes, and I can apply the usual Airhead theory, because then my inner pruned Airhead function is just the sum of the integer points in the open regions. And if I now assume that these open regions are integer polytopes, then I get a polynomial here, and the sum of a polynomial is a polynomial. So in this case, my inner pruned Airhead function is actually a polynomial.
So Sophie, I think so are these actually polytopes, or I think
Yes.
okay.
Um,
Can you just go back one slide real quick, and can you explain one more time how I should be thinking about this?
okay, first of all, think of a polytope, right? In this case, this polytope will always be a cube or a square. And then take some, well, first maybe take some hyperplane arrangement. This is what an inside-out polytope was. So you have a polytope and you have a hyperplane arrangement, and then you kind of cut out these hyperplanes of your polytope. Right, so what you end up with is still bounded,
Okay.
because you only consider points in your polytope, but you also take out some points from your polytope.
I see. Okay.
And here I want to take out points that are in these codimension 1 cones.
I see. Okay. Yeah. Thank you.
Thanks for the question. I unfortunately can't see you. I only can see like the first 5 people or so. Like, little annoying. Oh no, now I can see more. Oh wow. Ooh. Okay. Right. So are there more questions about this pruned inside-out polytopes or this counting function? Okay, then let me define the second counting function, the cumulative pruned Airhead function, where I now want to count integer points with multiplicity. So what I do now is I actually count all the integer points in the polytope, and then I want to see, okay, in how many closed full-dimensional cones of my associated fan are these integer points contained in, right? So here I would count 2 because it's contained in this cone and in this one, right? And this integer point in the middle, I would count 3 because it's, well, in 1, 2, 3 of my cones, of my closed cones that are associated. And you might see what I actually do is I count the integer points in the closed regions, right? If I think of these regions as polytopes and I take their boundaries and I count integer points in those closed regions, well, these integer points that are contained in more than one full-dimensional cone means they're contained in more than one region. So I count with the appropriate multiplicity. So my cumulative Airhead function, pruned Airhead function, is actually the sum of the Airhead counting functions for the closed regions. And again, if I assume these regions to be nice, to be integral polytopes, I get a polynomial. Okay, and now I can associate, like relate these two counting functions by reciprocity, which is basically just Airhead-McDonald reciprocity. So let me give you this one-line proof. So I start with this inner counting function, and I plug in t, and then from the what we've seen 2 slides before, if I assume to have, let's say, some k regions, I actually count the Airhead, like the integer point in the open regions, right? And then I can plug in minus t and adjust the sign and apply Airhead-McDonald reciprocity. And what I get is the sum over my regions, where I have the Airhead polynomial of the closed regions with positive t. And this is from the slide before, exactly how I defined this cumulative counting function. Okay. Are there any questions about this?
Can you tweak the counting function a little bit for half open and half closed regions?
Maybe. I don't know. I haven't thought about it.
And there's no way for sure that it will be a polynomial, right? Even if you have some sort of function.
Mm, mm, well, I think it might even be a polynomial. So I know that there's some kind of reciprocity if you have like half open triangulations and half open cones, and you like if you take out some facets on one side and you take out exactly the opposite facets on the other side, these are related, but I'm really I haven't really looked into it, but maybe I should do that actually. Okay, cool. Any more questions? Then let's move on to the application of generalized Computahedron.
Hello?
Yes.
Yeah, I have a question. I'm wondering if the what is gained by requiring those additional boundaries that separate the polytope Q into into open polytopes, be a fan, or if we could simply consider, say, a collection of open polytopes whose closure, a collection of pairwise disjoint open polytopes whose closure is a polytope.
That sound good?
In other words, I see a cool picture where you have the square is dissected into triangle and two tetrahedra. If you could simply dissect a polytope like that, with the without requiring the the additional the separators to be from a fan.
Yeah, you might be right. I guess this definition is very much guided by the application I want to talk about. So most probably you can even generalize this more.
This stupid thing.
Right. So we should have you so I can do.
And maybe I'll ask a question in the opposite direction, which is there anything special if you require that fan to actually be the normal fan of the polytope?
No, I'm pretty sure you can do this for any complete fan. That's how I've thought about it so far. Again, that I talk that much about normal fans is because of the applications I have in mind. But yeah, most probably this can be generalized further. Okay, great. Thank you for these nice questions and comments. So here's the application and the reason why I came up with this. So this is the reciprocity result for generalized Computahedron. So if we have a generalized Computahedron and we look at directions that have integral entries from 1 to m, and I count the number of these directions such that the y maximal phase is a vertex, right? So such that they are generic, then this agrees with a polynomial in m of degree d. And if I plug in a negative integer, I sum over these directions with integral entries from 1 to m, and I count the number of vertices of the maximal phase in this direction. So for every such direction. And I now want to convince you that this is an application of pruned inside-out polytopes, right? So roughly speaking, what I'm counting are integer points in this cube in the dual space that do not lie on lower dimensional cones, that only the ones that lie in full dimensional cones. Okay, let me give you the details. I'll find my notes. I'm sorry. Here we go. Okay, so this is what we want to prove, right? We have this counting function and we want to prove that this is a polynomial. So let's look what this actually means. So I was already mentioning this, so let's write it down. What do I mean by this? This is the set from 1 to m to the power of d, which means I can look at the interval to the power of d, which then is a cube. So interval to the power of d gives me a cube, and intersect this with the integer lattice, right? And the direction being p generic means that the phase in this direction is a vertex. Okay, so we can rewrite this as being the number of points in this cube intersected with an integer lattice such that py is a vertex. Okay, so what does this mean? If the maximal phase in direction y is a vertex, this means that y is contained in the normal cone of a vertex in this normal fan of my generalized Hemodihedron, and these are full dimensional, right? So this means y is not contained in any cone of my codimension 1 fan of the generalized Computahedron, right? And let's rewrite this part a little. So if I want to count the integer points in the cube from 1 to m, maybe let's look at the picture here. If my origin is here and I want to count from 1 to m, I can as well count in the interior of the cube from 0 to m plus 1, right? So this is the same as counting from 0 to m plus 1 open and intersect with the integer lattice. Well, and this is nothing else as the m plus first dilate of the unit cube, the open unit cube, right? So what I'm counting is points in the m plus first dilate of the open unit cube, where I take out the codimension 1 fan of my generalized Computahedron and then intersect with the integer lattice. But this is by definition my inner pruned counting function for the open unit cube, the codimension 1 normal fan of my generalized Computahedron and the m plus first dilate, right? So, and now we just need to convince ourselves that if I intersect the braid fan with the unit cube, that this is integral. And then we get a polynomial. Okay, and for the second part, the reciprocity, so the statement is up here. So we have just shown on the slide before that if I plug in m, that this is my inner counting function for the open unit cube, codimension 1 of the normal fan of the generalized Computahedron, and m plus 1 here, right? So now I can plug in minus m and adjust the sign. And I can apply the reciprocity result for pruned inside out polytopes. So, oh yeah, so minus m plus 1 is the same as minus m minus 1. And then I get here the cumulative counting function for now the closed unit cube. The fan stays the same. And I have m minus 1 here, right? So this was defined as, well, I guess I'm cheating here a little, but let me first write down. I sum over these directions in this cube intersected with the integer letters, and I take the multiplicity of 0, 1, and the codimension 1 column of y. So why am I saying I'm cheating a little? Because I'm not cheating. I'm just not being precise. So what I have here, actually, I'm looking at the cube from 0 to m minus 1, right? And I intersect this with this integer letters. And down here, I'm let me write this in a different way. So I also want to take out this codimension 1 fan, my generalized Computahedron. And I say that this is essentially the same. I talk about what I mean by essentially in a bit, as looking at the cube from 1 to m and taking out this codimension 1 fan, because this is what I'm doing from here to here, right? And by this I mean, well, I have the same number of integer points, and these integer points, they have the same multiplicity. Why is this true? So this is a property that comes from the Braid Fan, because the Braid Fan contains this line where all coordinates are equal, right? And along this line, I shift my cube. So by shifting this cube along the line, well, first of all, I of course maintain the number of integer points because they just shift by an integer vector. But also the Braid Fan is invariant by these shifts, right? The cones are the same. They all contain this line. So I can do this shift. And now we just have to rewrite this a little more. So I'm summing over these directions. Well, and this multiplicity was defined as being the number of full-dimensional cones in my fan, in this case, my normal fan such that the cone contains y, right? But this is nothing else than saying, well, this is the number of vertices of the y maximal phase, right? Because the full dimensional cones correspond to normal cones of vertices. And this is what we wanted to show. Okay, and then we can generalize with the same method to arbitrary dimensions, right? So for k from 0 to d minus 1, I can say, well, let's count these directions such that the y maximal phase is a k phase instead of a vertex. So k equals 0 corresponds to the case from the previous theorem. And then we can say, well, this is a polynomial of degree d minus k. And if I plug in minus m, I adjust the sign. I'm counting over all these directions, but now I'm counting the number of k phases of the y maximal phase. And the proof works along the same lines as the one before. It's just a little more technical and involved because you have to be careful with the dimension and include and exclude some cones, but the method is the same. Okay, I guess that's what I wanted to talk about today. Yeah. So I hope I could convince you that we can use pruned inside out polytopes and generalized Computahedron to prove this result and give a more general version of it. And yeah, this I would like to thank you for your attention, and I'm happy to answer any further questions.
Awesome. Thank you, Sophie. Let's thank Sophie by reacting or unmuting.
Okay. Thank you. Yeah.
Thank you.
Are there any questions for
I had a quick question. It might just be sort of a terminology thing, but when you say it agrees with a function of a certain degree, is that different than being one, or is it just sort of like a subtle thing?
So my counting function is in the beginning only defined for integer points, right?
Oh, I see. That makes
So,
sense. Yeah.
I don't really want to compute it for 1/2 or something.
Yeah. And I guess you can't really say it is a polynomial if it isn't defined in so many places. Yeah. Makes sense.
any other questions?
Yeah, hello. Let me apologize. I had a headphone problem. Oh, Sophie, I saw that you answered my question, but I didn't hear it. So I'm wondering. I asked the question. When you presented the main reciprocity result, why the the dissection had to come from a fan.
Yeah, so let me repeat the answer.
Yeah, thank you.
I'm not sure it really has to come from a fan. So this definition is motivated by the application I had in mind. So you're right. Maybe we can extend this even further to your general setting you were proposing.
Okay, thank you. So the following results were dependent upon the dissection coming from the fan.
Yeah, exactly.
Yeah. Oh,
There
cool. Thank you.
I was considering the normal fan of the generalized Computahedron.
Yeah, because the subject was generalized Computahedron. Thank you.
I have a question, Sophie. Do the reciprocity results look nice when you're thinking about the Earhart series? And I guess it's a two-part question. And does it matter? Like, would we even care to think about the Earhart series for these things?
I haven't thought about it. So, yeah, maybe, I don't know, the way I think about Airhead theories is like a very compact way of having all the information. I guess this applies here as well. Although, as far as I know, it's pretty hard to compute these polynomials. So I guess it's also pretty hard to compute the series. But maybe it's easier. Maybe we should try. I don't know.
Yeah. Sometimes, I mean, I don't want to push Earhart series on anybody, but sometimes it's easier to think of. That's fair. Are there any other questions for Sophie?
I have a question, and maybe this just comes from me not knowing that much about reciprocity theorems, but I'm curious if, like, do you think that reciprocity, these kinds of combinatorial reciprocity theorems always have some like interpretation like this lying in the background, or is this just like a special case where you have this interpretation? It's more of a philosophical question, I guess.
Yeah, I mean,
yeah.
I actually find this super curious how these things relate, right? So this is a completely different approach here, and yeah, I don't know. These are like two approaches from two different worlds, and they give you the same thing. So yeah, it would be interesting to find out, like, is one word contained in the other, or are there cases where it's disjoint?
Yeah, I have a comment. I would think that that question boils down to whether there are any reciprocity theorems that do not result from the reciprocity property of Earhart polynomials. So yeah, and of course, all of these results, your results, and the inside out polytope results are built out of the basic Earhart theorem, in that the polytopes in question are formed are formed by an array, by a union of subpolytopes to which the basic Earhart theorem applies. But I don't know. I don't know if my knowledge isn't wide enough to give a reliable answer. But whether there's any kind of reciprocity that comes from principles other than, or whether the reciprocity that doesn't come ultimately from Earhart's theorem.
I guess it would be nice to come up with an example, but then it would be super hard to prove that there's actually no Airhead theory hidden somewhere there.
I guess one specific example, and I do want to mention to anyone who has places to be, it is right around the start of the hour now. So one example of the first one I heard about is this n choose k versus n choose negative k, being like ways to choose k things versus ways to have a certain number of things in different categories. Does that have a connection to Earhart theory?
I have definitely seen a proof using Airhead theory, but I cannot tell you how it went. But Cesar Ceballos, or however you pronounce him, showed it to me once.
Cool.
Maybe Max can tell us.
Yeah, yeah. That was my impression as well about that that reciprocity result.
Yeah, I think it might be related to reciprocity of the simplex, but I could be confusing that with something else.
No, I think that's. Are there any other questions or comments?
So I have a question, but I can wait until after the recording is over because it's sort of an involved question to ask.
Well, let's before we thank Sophie one more time, and I know Emzai just stepped out, but so Emzai Jeffs at the University of Washington is going to be our next week's speaker, and he'll be talking about convex codes, realizations, minors, and embedding dimensions. And so we hope that you can join us for next week. And with that, let's thank Sophie one more time and then end the recording.